Aloha. Welcome to this session of Shadow the Scientist, exploring the universe with the Gemini North telescope. My name is Jamika Marshall, and I am pleased to serve as the Shadow the Scientist Programs Manager. Joining me for this fantastic session this evening are our science hosts, Aaron Figura and Emily Peavy. Also, our amazing observing staff here at Gemini North, Denise Hung is the operator for this evening, and Layla Alamos is in the observer's chair. We also have special guest, Andy Stevens. Now, for those of you who are just joining us for the very first time, welcome. Shadow the Scientist is an initiative that is brought to you by a group of amazing people at the University of California at Santa Cruz. Now, the International Gemini Observatory is located on Hawaii's Maunakea as part of an international community of observatories that were built to take advantage of the superb atmospheric conditions on this long dormant volcano. Now, Gemini consists of twin 8.1 meter optical infrared telescopes. And of course, they're located in amazing places. Gemini North here on Mauna Kea, and then Gemini South on Chile's Cerro Patron. Now, by incorporating technologies such as laser guide star, adaptive optics, and multi-object spectroscopy, astronomers in the Gemini Partnership are able to explore the universe in unprecedented depth and detail. Now, as I said, we are going to be shadowing two people, but there are three people in the control room, and we're going to get introductions a little bit later. First, I'd like to go over to our science hosts, that is Aaron Figura and Emily Peavy, to get us started. Welcome, Aaron. Welcome, Emily.
Hi, Jamika. Thank you. Welcome everybody. I am Aaron Figura. I am an astronomer, and I work here at Gemini North as an operator and as an observer. So I normally will do the same roles that we'll see Layla and Denise in tonight in the control room. But tonight I get to be your science host and just tell you a little bit about what we're doing tonight and give you a little context and answer questions.
Aloha, everyone. My name's Emily Peavy. I'm the Senior Education and Engagement Assistant here at Gemini Observatory / NSF's NORLab. My job is to kind of be the communicator, think about the best ways that we can take some of these really, really complex ideas and make it them a bit easier for us to understand so that we can all have a better chance being able to understand all the wonders of the universe. I will say Charlie knows a lot more, Aaron knows a lot more about the amazing things and how we are figuring out all these amazing things of the universe and a lot of the technical sides. I'm going to be leaning on her for a lot more of this, but we are just so excited to be sharing the universe with all of you tonight.
Fantastic, fantastic. Thank you, Aaron. Thank you, Emily. Aaron, what's happening in the control room? Like, could we over there for quick introductions, or are they busy? Lots happening.
I think it looks like we can. Let's see if we can bring them up. Control room, do you have a moment to talk to us?
Hi, I'm Layla in the control room. Face. And this is Andy.
Why don't you got a few minutes that you can talk to us here?
Sure. Yeah.
All right.
Got a few minutes.
Would you tell us a little bit about what we're doing right now? What's going on with the telescope?
So currently we are observing a supernova. We're taking a spectrum of the supernova at the start of the night. It was a high priority target and it's currently setting. So, but right now we have some really good seeing, some scattering clouds, and the data is looking good.
Fabulous. All right. So Layla just mentioned something called seeing. Describes essentially how good the view is, how clear the air is. We'll talk a little bit more about that later on this evening. We always have to adapt to changing weather conditions. So when we have very good conditions, we want to take advantage of those as rapidly as possible. Make sure we're not wasting the really good skies for our science. Layla, what do you do as the observer?
So as the observer, I will take the plan for the night. Every single day, there's a plan that is made, and I will fit the programs to take data from, and I will kind of judge based on the conditions we have for the night, which program would suit those conditions best. And then I will set up the acquisition of the target. I will take the data of the target. I will look at the data afterwards and make sure if it's good data, if it's usable for the scientist who the data is going to. And I will also keep a log of what we are looking at throughout the night, and it'll help the scientists during the day to kind of see see how the plan went throughout the night.
Great. So Gemini Observatory is a little bit unusual from many other observatories. It's been common practice, certainly in years past, and still is at many observatories, to operate in what we call classical mode. In this mode, researchers will come to the observatory. They'll propose. Usually, most observatories have some kind of open proposal submission process. So you can, as a researcher, make a proposal. I have a task that something that you want to do. You have something you want to look at, some scientific idea that you want to investigate, and you make the case for how well the telescope can answer that question. How much time you're going to need, what instruments, what cameras you'll need to use to collect the data. We have a TAC, a telescope allocation committee, that goes and evaluates those and ranks them and selects some of them to actually get observatory time, get telescope time. This is fairly common across many observatories. Where things change is what happens next. That next step for a classical mode is that the researcher themselves will come to the observatory. They'll get assigned some time. Your time is the last week of September, for example, and they'll actually physically travel to the observatory. They will sit in the control room and actually collect their own data. Now, there's pros and cons of this method, but we don't operate that way. What we do is we use what's called queue scheduling. It's a dynamic scheduling system, which allows us to make changes based on what the weather conditions are. So if you get assigned telescope time, you need really clear skies, and your time that week of September that you're assigned to, if that's all cloudy, that was your time. And so that's what you got. With our queue scheduling, the researchers are going to submit all their research proposals. They're essentially going to write up little observing programs, and those programs will tell us where to point the telescope, which instrument to use, how many images to take, how much data to collect. It'll tell us all of the configurations that we're going to need. And so then we are going to look at all of the observations that we have, look at the weather conditions for a night, and we get to pick which observations best fit the weather conditions that we have. So if you've got a program that requires really, really good weather, you're going to get really, really good weather. It just may not be tonight. It may be tomorrow. It may be next week. It may be next month. But we're going to make sure we get that because we have this flexibility. So in our control room, Layla is acting as our observer tonight. We always have a staff observer. Generally, it's either one of the group of what we call science operations support people. That would be me, that would be Layla, that would be Denise. We also have scientists on staff that sometimes take a turn as observer as well. So that's the role Layla's doing tonight. She's keeping an eye on weather. We'll talk about some of the weather that we have to deal with, that we have to keep an eye on and how we do that here in a little bit. Denise, can you tell us a little bit about your role?
And so I'm the operator for tonight. I basically do everything with moving the telescope physically. So whenever we have a new target to go to, I'm the one who moves the telescope to that target and it's set up our guiding so we can get a nice clear image of the target. And if anything goes wrong, then I'm also on task to handle it. So yeah, I'm in charge of making sure the telescope's safe and operating smoothly.
So Layla's not the only one watching the weather. You are too, but for different reasons.
That's right.
We have
Yeah,
limits.
if the weather turns like especially wet, then we can't operate in those conditions because the telescope uses a large mirror and that mirror is coated with a special kind of coating to keep it very reflective. But if it gets wet out there, like if it rains, that coating can potentially wash off. So we want to like close up the dome in that case if the humidity spikes or fog rolls in or anything like that.
Right. We just had some weather concern. You just had some environmental concerns earlier this evening, didn't you?
Yeah, so earlier when we were first opening up for tonight, the dust levels were pretty high. And dust is a concern because like, well, those particles can get like embedded in the mirror, but the bigger risk is if it combines with like the moisture in the atmosphere. And in that case, it could precipitate out as acid rain. And we definitely don't want that falling on our equipment.
Right. But the dust has gone down now?
Yeah, it looks like it's down back to normal levels.
And obviously we keep a watch on those all throughout the evening. Thank you, Denise. Thank you, Layla.
Thank you.
So maybe I can talk a little bit here about some of the weather conditions that we monitor on a regular basis. I'm going to share a screen with you over here. If I can remember how to share.
And while you're doing that, Aaron, I'd just like to, again, welcome everyone to this session. I apologize. Some other people joined while I was in the control room a few minutes ago and they were waiting to get in. And that includes the founder of Shadow the Scientist, Raja Guhathakurtha, who is with us. So thank you, Raja, for joining us. And thank you all for being here. Again, my name is Jamika Marshall, and I am the Shadow the Scientist Programs Manager. I see that we have people from joining us from Molokai, so that's the Akaula School with Vicky Newberry. We have participants from Hyderabad in India. We have the Netherlands. We have the Memphis Stargazers, Massachusetts, New York. Let's see, we also have people from Hilo, which is absolutely wonderful. And some who just sent me from North Carolina. Okay, wonderful. So please feel free to introduce yourself in the chat. We already have some questions going on, coming to us about Comet 3I, which Emily has already answered, but perhaps Aaron and Emily will speak to that a little bit later.
Yeah, as Aaron's pulling up some of the stuff that we're currently doing, we did a phenomenal Shadow the Scientist session regarding 3i Atlas right at the end of August. And I think that video has been like watched like 70,000 times according to YouTube. And it was an amazing session to be a part of. I put the link for it in the chat. And it was an amazing session since we were able to bring up the data and start seeing the tail in the raw data, which was nuts. Like you don't often see stuff like that in raw data. So Comet Atlas, I was just checking the orbit viewer for it. It's getting a bit close to Mars, but it's also starting to get close to the point where the sun is going to be in the way for us little earthlings stuck here on our planet in order to be seeing it. So we are approaching the time that we're not going to be able to see it. However, I do know that there's interest in November for us to have another Shadow of the Scientist session when it's on the other side of the sun. We can start observing it in the daytime. So keep an eye out on the Shadow of the Scientist website for not just that, but all amazing Shadow of the Scientist programs that are coming up. So it's an amazing thing to be a part of.
Oh, thank you so
Excellent.
much, Emily. I really appreciate that. Yeah, please do join us back again in November. I was just talking to that one scientist that we're hoping to have that session with a little bit earlier today. So it's in the works, you all. It's in the works.
Good.
Thank you, Emily. Aaron?
Yeah, so what I was going to show you a little bit about is how some of the ways um, that we monitor weather. We are actually sitting in Hilo right now, which at an elevation of a few hundred feet above sea level, actually, where we are. We're a little bit up the hill from the actual coast. But we're operating the telescope remotely from the summit. The telescope is at the summit of Mauna Kea. It's at an elevation of about 4,000 meters, about 14,000 feet, and it is difficult to work up there, to be very honest with you. I love operating from the summit, but you have much less oxygen. You are sitting above about 40% of the Earth's atmosphere, so your atmospheric pressure is 40% less, which essentially means you're getting 40% less oxygen into your lungs as you breathe. So that has a lot of health effects. You will tend to get tired from very simple activities much more quickly. You can get lightheaded. You can get sick. Depending on how well you are adapted to the elevation, you can get physically sick, and it's just very uncomfortable and can be life-threatening if it becomes severe. So there's a lot of advantages to operating remotely here from Hilo. I think my favorite is that I can be home and in bed in 10 minutes when the night's done. Is my personal favorite. There's a lot to be said for sleeping in your own bed at the end of the shift. But that does mean that we need to have a lot of ways of looking at the weather conditions at the summit. And what you see here is a web page that we use. This has a lot of the data that we use to keep an eye on the conditions at the summit. So probably the first and most exciting thing are our cloud cameras. And so each of these little animations here is a 15-minute loop showing the last 15 minutes what the sky looks like. And so we can look at these and we can get a feel for what kind of conditions we're in. So what we see here is that we've got some high cirrus clouds, some thin high clouds there that you can see sort of center of the screen and a little bit above. You also see the inversion layer, this floor of clouds. That's sitting down around 9,000 feet or so. An inversion layer is an atmospheric temperature inversion. It helps keep the air that is down around sea level down there. So we don't get warm, moist air coming up to the summit from the ocean. It's basically trapped below that inversion layer. that inversion layer can move. So we see it at a nice low point right here. Sometimes that inversion layer will raise up, and so we'll see those clouds come up and start actually creeping over the eastern plateau, a lot of the dark area that you see in that east cloud camera image. And that's when we need to start being very, very careful, because it means that we're likely to see a big increase in humidity and potential fog and precipitation if that rises much more. But we have 4 cloud cameras that are pointed in 4 different directions, covering a good chunk of our horizon. So we can look and see which direction stuff is moving, what's coming in. Does it look like chances of precipitation? But we also need to know, keep an eye on the clouds, not just for, we need to keep an eye not just for the sake of protecting the telescope and possible precipitation, but for evaluating which programs we're going to observe. Some science programs need very, very clear skies if they're looking at a very, very faint target, for example. Other programs can get away with a little bit of clouds that you can, enough that you can see through. And that's part of the way that we rank our science programs. So you can see in these cameras.
So I want to point out, as we're looking towards the west here.
Yeah, let me get to
you
West Cam.
See, the #1 source of light pollution on Mauna Kea, nice and big in that image. What do you guys think that is? It's not the sun. It does look a lot like the sun in this. That is the moon.
Could it be the moon? Oh,
Yes, yeah.
I'm a little late.
It is the moon. And even tonight, like the moon is a very, very, very thin crescent. I looked up what Hawaiian phase it was earlier today and I already forgot it. But it's a very, very thin crescent. The new moon Muku was just a few nights ago. And even with that thin crescent, that is how bright the moon is.
Right.
Even just on our cloud cameras. So you guys can imagine that the moon can be the #1 source of light pollution. And as Aaron was just mentioning, that when you are putting together your science over what are the conditions in the sky. Oh, wonderful. Someone said no Hokai is the name for the phase of the moon for tonight. Excellent. Thank you for
Thank you. Mahalo.
Yeah. It's so bright because it's reflecting sunlight. Yes, exactly. And it is close. So it's not just that it's reflecting sunlight, because all the other planets in our solar system are also reflecting sunlight, but it's also that it's so close to us as well that makes it super, super bright in the sky. Now, if you are putting together science, oftentimes moon phase is what might be something that you are considering. If your object is really, really faint and you need the darkest skies, you want to be scheduling that time when the moon is not in the sky. However, if you can afford to have a little bit of light pollution in your sky, then you might be looking at a different moon phase. Although the moon's going to be setting pretty early tonight. You can see that that's our camera that's facing towards the west. So sunset's going to be like within the next half hour.
Yeah. One of the other things to note is the moon. Moonlight is going to affect in a couple of ways. One is it's going to illuminate all of the things that are in the sky. So, it's going to give some background brightness everywhere you point the telescope. It's certainly going to be worse, more exaggerated right near the moon. If you take a look here at that west cloud camera image, the stars around the moon kind of fade out. They're not nearly as sharp and distinct. They're much harder to see. And that's just that light pollution from the moon that is so much stronger than the actual starlight is. I'm going to point out here, obviously we are on the summit of Mauna Kea. We can see a couple of the other volcanoes of the island here. In the south camera, there is you see the long slope of Mauna Loa over to the right. And in the west camera, we have Hualalai. And I think that's all we can see tonight. If the weather is clear, we can often see Kohala from here, and Haleakala as well, but not tonight, not with the inversion layer where it is and the clouds what they are. So we use the cloud cameras to evaluate weather conditions. We look at satellite imagery to look at sort of the bigger picture to give us an idea of what's coming in the next few hours. Sometimes that's a matter of are we going to see bigger, more cloud cover in the next few hours? Is there possible precipitation activity in the next few hours? Sometimes it's the reverse. We'll look at that to figure out if it's going to clear up in the next few hours. So we have all of those tools. And the other ones I'll mention on here are the plots over on the right-hand side. And those are going to give us a little more, it's going to give us a little more information that we're going to use to pick the best science for the conditions. So that top plot over here to the right is a measurement of cloud cover, how we evaluate how much light is being absorbed by clouds, and we can use that to rank to pick the best. We have a lot of programs that depend on cloud cover. Water vapor. Water vapor isn't clouds. Water vapor has more to do with gaseous water in the atmosphere. When you're looking at a cloud, you're looking at actual liquid water in the atmosphere, little water in the form of liquid droplets. The water vapor here is a measurement of how much gaseous water there is, and that's very important to know when you're doing spectroscopy. These two plots, which are not, I think we've got a couple of data points down here, are evaluating seeing. So I mentioned seeing before. Let me give you a little bit of better explanation of what seeing is. Seeing describes, let me tell you what poor seeing is, actually, would be the easiest way to do it. When you look across a parking lot, for example, in a bright, hot summertime, you'll often see that shimmer effect as you look across the parking lot. Everything that you see over the parking lot looks kind of shimmery and wavy. What you're seeing is turbulent air. You can't see the air itself, but different temperatures of air and air that's moving around turbulently can refract light in different ways. And that happens when you have this strong heat source, the parking lot, which is absorbing visible sunlight and re-radiating infrared light. And that's heating that air, and it's causing the air to stir up. And that's what that is. When you look at stars at night and you see them twinkling, it is exactly the same kind of shimmer that you're seeing that you see across a parking lot. It's not due to really, really warm air over asphalt, but it is due to that turbulence in the air caused by those temperature differences. What that shimmer does when you're taking a astronomical exposure, when you're taking an image with a telescope, is it ends up smearing the star out. So instead of being a pinpoint, the star looks like a blob. So seeing describes how much of a blob it is. So a very small seeing value means that it's much more pinpoint-like. That's what we want. A large seeing value means it's more blobby. And generally, that's not what we want. But what we do with these plots is we can evaluate how blobby the stars are. So that's probably the best way of describing seeing. It's how blobby are the stars.
We had a question in the chat of what are the graphs on the right side represent, and each one represents something different. But the one that's kind of centering the screen right now, that is the graph that is going to be representing the seeing. Although you can see that we haven't taken a seeing measurement.
So yeah, so that one is the one that's titled CFHT WX Tower Seeing, is seeing measurements from a measuring device at our neighbor telescope, the Canada, France, Hawaii telescope, who actually having a Shadow the Scientist session tomorrow. So if you're interested in seeing what a different observatory looks like and how they operate, definitely sign up for that. Get registered. Get registered now. It'll be a good time for a Friday night. Actually, the plot below that one, which is titled Effective 500 nm AM corrected, that is seeing measurements taken by our telescope here. And so the data points are kind of faint here, but there's a data point way up here around 1.4. That's pretty blobby. That's pretty lousy. But we also have some measurements more recently. They're sort of down in the 0.4, 0.6, around 0.7 range, and that's not bad. We definitely are glad to see those kind of measurements. So right now, seeing is pretty decent. We expect seeing is going to get, our forecast suggests that seeing is going to get worse as the evening goes on. So I know that our night crew is working really hard right now to get that high priority science done quickly. And then our bottom two plots are just show us actual, what most people would think of as weather conditions: temperature, RH is humidity, wind speed, wind direction, and then this bottom plot are particle counts. And so you can see that spike in particle counts at the start of the night that had us a little bit concerned about telescope safety. So
So,
that shows you a little bit of the tools that we're using to evaluate both weather conditions for safety and weather conditions for the actual observing process.
so Aaron and Emily, could we take a look maybe at the telescope control system to kind of get our participants oriented
Yeah.
with how Layla and Denise, what they're looking at on one of the control room
Absolutely.
screens?
All right, give me just a moment here to pull up the right screen.
Thank you. And for everyone else in our audience, thank you for the great questions. Thank you for sharing where you're from. I really appreciate that. And it really helps us to get to know you, and knowing where you're joining us from helps to make sure that I keep all of the amazing places that we reach in mind. It's really amazing to bring people together from all around the world over their love and interest in astronomy. So thank you.
All right. All right, so I'm gonna let me share again here.
Please.
I am going to always have to talk it out. All right. So I'm going to show you a couple of things here. So what you see, whoops, that was not what I meant to do. All right. And I'm going to actually shrink this so you can see. So what you have here is one of the status displays that we use. We have many applications that we use to control the telescope and control the observations. These are all home built pieces of software. These were all coded by Gemini programmers over the past 25 years of Gemini's operation. So this one is showing the status of the telescope right now. So it's showing us the current RA, right ascension and declination. Those are astronomical coordinates. You're probably more familiar with azimuth and elevation, so that's how we can specify direction on the surface of the Earth. The plot down here is showing you which direction the telescope is pointing. It's showing us that the shutter is closed up really close around the mirror. So we can open that shutter, that slit that the telescope looks through. We can open that up very wide and let us give us lots of airflow, or we can close it down fairly tightly. And we choose that basically depending on what kind of wind we have. We don't want a lot of wind on the telescope. That makes the telescope shake and takes and degrades the quality of the data. So here we're closed up pretty tight. Wind conditions, it's a little windier, so we've got it closed up, open just enough that we can see through. excuse me. To the right, you can see a sort of a schematic diagram of the telescope and the beam path. So light comes in from the top, reflects off the primary mirror to the secondary, and it actually reflects from the secondary down through a little hole in the primary mirror, in that big mirror, down to our instrument support structure. One of the other things that Gemini is really good at and a little bit unusual at is we have the capability of using any one of 3 or 4 instruments to collect data over the course of the night. So on many telescopes, they're going to have one instrument that they can use at a time at night. Changing instruments is a task that takes that takes hours long during the day to do. Sometimes that means instruments have to be physically removed from the telescope and then other ones reinstalled. But in any case, you know, you've got many telescopes have a very limited number of instruments. We have generally 3 to 4 that are on the telescope that we can choose at any given time. And it takes about a minute or two to select between them. What that means is we can do imaging in the visible light. We can do spectroscopy in visible light meaning the light that you see with your eyes. We can do spectroscopy. In spectroscopy, we're breaking the light up. We don't see a pretty picture. Instead, we see kind of a rainbow. We're breaking the light up into a rainbow of colors because each of those individual colors can tell us something about the source. We can learn about composition. We can learn about motion. We do a lot of discovery of exoplanets, planets around other stars, by careful analysis of the spectra, the light from that star, by breaking it up into all those colors. James, I see your question right there. Yes, we cover from the visible band and we can get up to the mid-infrared. So if you know the visible light covers wavelengths of around 300 nanometers up to around 600 nanometers. So we have that, but we also can cover near infrared and into mid infrared up to about 5.4 microns. Most of our work is done in visible and near infrared. I don't think we've done mid infrared work for a number of years right now. But we can choose, you know, if you want to look at an object like Comet 3I, you may want to look at it in the visible, you may want to look at it in the infrared, you may want to do imaging, and you may want to do spectroscopy. You may want to do all of that. And if you've got the time, you could conceivably do all of that in one night because we can switch between instruments fairly rapidly. So what you see on this diagram that I was talking about, light comes down from the secondary mirror through that hole in the primary and is reflected off of the tertiary mirror, the science fold. And each one of these numbers, 1 at the bottom, 2, 3, 4, 5, represents a different instrument that light can be directed to. And basically switching between instruments is more or less as fast as rotating that mirror to direct light to a different place.
That is something that really separates Gemini from other similar observatories, is that we can have up to 5 instruments on the back of the telescope at a given time. Most of our neighbors at the summit of Mauna Kea and other observatories will have 1 instrument on the telescope at a time. So if any switching of instruments is a whole ordeal.
It's an ordeal. And to be fair, I mean, there are pros and cons with each system. With these other telescopes that usually have 1 instrument on the telescope at a time, those instruments can be a lot bigger. We have to hang 5 instruments off the back end of our telescope, and they have to be small enough to be moved around on the telescope and to, you know, for us to hold that weight there. So there are limits on how, you know, essentially on how good the instruments can be. So we pay a little, it's kind of a min-maxing game. We trade off some capability for a single instrument versus the flexibility of having lots of instruments.
Can
So
I
there's sort of a
show-
room, there's an importance for both approaches, but this is what we do.
Can I show an image that has people in it along with kind of the instruments mounted to
please.
give our audience an idea of what this looks like as you both so brilliantly described it. Let me just share my screen here.
Oh, fabulous.
So they're sitting underneath the instrument support structure. So this is underneath the telescope.
That's right.
Yeah.
And we can see how many instruments are here. I see Altair clearly.
Yep. So the blue
Yeah.
box, the blue box and the black, the blue and the black above it are Altair, our adaptive optics unit. So that's in one of the instrument bays. It is not a data recording instrument in and of itself. We're going to use that to get the very best seeing conditions that we can. We can correct for some of the effects of atmospheric turbulence through the use of our AO system. So that's what that is. Over on the right, you can see a box there and kind of a truncated cone shape. That all of that there is GNIRS. That is our near infrared spectrometer, which is also capable of some imaging as well. Let's see, you can't see the other side of it, but we have GMOS on the other side, and what would have been hanging off there? Oh, GCAL. So we have two of the bays that are generally taken up by non-data recording instruments. One is Altair, and the other is GCAL, which is basically a calibration source for it. It has a bunch of different known light sources in there that we can use to calibrate our instruments with. So usually we've got those three other bays that we can use to attach data recording instruments. And I should be clear here because I keep using the word instrument. The instrument here is the thing that's actually recording the data. So instrument here means kind of what you probably mean when you say a camera. Optically, camera means something slightly different. It's all the lenses. But think of it that way. GMOS is a camera that's about the size of a minivan. GNIRS is a camera that's about the size of a compact car. The other instrument, I believe that image was the IGRINS commissioning or installation image.
It was.
IGRINS is an instrument way small. IGRINS is an instrument that is about the size of and has about the appearance of the Ark of the Covenant from Raiders of the Lost Ark, if you've ever watched that. First time I saw that instrument, I just had to laugh because it's a gold box. So it's really small. It's very unusual for our instruments. Most of our instruments are as big as we can make them.
Now, Aaron and Emily, I saw our special guest there, Andy Stevens, was just over talking to Layla. Can we potentially check in with the control room, maybe
Absolutely.
see what they're seeing and talk about one of the targets?
Okay. Actually, currently we are looking at a kilonova right now. Very cool.
Very cool.
I don't know if you guys are allowed to pull up the data so that they can see what we are seeing, but it is an imaging sequence and it is looking quite amazing. And Andy was just talking to me about what we're going to do next, which is going to be a sort of test run with new software that we're trying to implement here at Gemini, and we were just talking about that. And that's going to happen next after we finish observing this kilonova.
Ah, I see. Thank you for the update,
What a
Layla and
kilonova is,
Andy.
just because
Yes,
and
I
I'm
was
gonna,
going to ask you that, Emily.
Yeah,
What is a
okay.
kilonova?
and
While
while
Aaron
you're
pulls up
doing
the
that,
image.
and while you're doing that, I'm gonna show, I'm gonna actually show you what the data, what we see.
Okay, yeah.
Ah,
Okay.
ooh.
Okay.
So if I just give a little bit of explanation, we're used to seeing the really pretty pictures that are published and, that we see in the media. This is, we just loaded a new image. Sorry. This is the raw data. This is what it looks like when we first collect the data. It takes a lot of processing to clean it up and to generate the pretty pictures that you see. And have no fear, that will be done with this, or that certainly could be done with this. But the pretty picture is not the goal of the astronomer. But here, what you see is it's actually monochromatic data. It looks like it's sort of blues and purples and yellows. That is just a color map that we use to display the data. When we collect image data, we're essentially the detector in the instrument is a monochromatic detector. We can make those pretty pictures by using colored filters. So right now, let me actually take a quick look and see if I can tell you what filter we're using. So right now, this is actually showing us green light. This image is on the G filter, so it's showing us green visible light, basically. And then we can take an image with a red filter, and if you take an image with a blue filter, and we can actually combine those to make the color image that you know and expect. So our kilonova, oops, let me go the other way. Not too far the other way. Ah, I just can't win, can I? So right here in that middle of the frame, we have our target. I'm going to see if we can take a little look. So this we're seeing a galaxy. We're seeing that galaxy more or less edge on. I'm going to see if we can actually find the kilonova itself.
Oh, wow. So you changed something about the image. How did you change that to make it more
So yeah,
granular?
so what I'm doing is I'm adjusting contrast levels. So basically, I remember the old days when everybody knew what the contrast knob was because you had it on your TV, and that was before most of you were born, I'm sure. So this is our galaxy. Or not our galaxy. This is a galaxy that should be host to the kilonova. The nucleus, the core of that galaxy is there. And I don't, looking, if I'm correct, and that's our kilonova's host, I can't make it out just by eye here. It may be the brighter knot over here, possibly. All right, Jim, thank you for not making me feel that old. I appreciate that. Yeah, you want to talk a little bit about what a kilonova is, Emily?
Yeah, just because, yeah, sorry, I had my chat closed and then I opened it up and a bunch of stuff just popped up questions. Does Mauna Loa cause light pollution? Mauna Loa does not actually cause that much light pollution. While Mauna Loa is an active volcano and it is right across from Mauna Kea, it is not actively erupting. So Mauna Loa doesn't really cause that much light pollution. Sometimes we do get a little bit of light pollution from Kilauea, but my understanding is it's pretty negligible. It's not something that is really messing with observations.
Yeah, Kilauea, if we have strong cloud cover over Kilauea, in that lower deck, that cloud cover will light up. But you have to be looking sort of in the right direction at a very low elevation for that to have any significant impact.
Is that Andromeda? To me, that doesn't quite.
No, that's
that
not
looks-
in,
that
that's
looks
not
a bit-
Andromeda.
That looks much farther away than
Mm.
Andromeda in our image. But I don't
And
think we're allowed to say what galaxy it is.
Yes, exactly. I put that
but-
in, I put that
Yeah.
part in the chat as well
Yeah,
too.
so,
yes.
I will say, like, to our naked eye, Andromeda does look like that big in the sky, though. But for these telescope eyes, Andromeda would appear much bigger in these images.
Yes.
Yeah.
Yeah, yes, it would.
Okay, but kilonova, since kilonovas are so sick, they're so neat, sort of thing. And I'm gonna get to one thing that just blows me away about how common it is right now, compared to a few years ago. But anyway, but backing up a little bit, a kilonova is a collision of two neutron stars, and neutron stars on their own are also super, super, super wild. So when you have a very, very massive star that is coming to the end of its lifetime, that massive star will die in a supernova. And we often think of supernovas as being explosions, but supernovae start off as a collapse. And I always like to describe that all stars are balancing acts. You have the gravity, the mass of the star that is pushing in, and that mass, that gravity pushing in, needs to be balanced by the energy that's being created in the center of the star pushing out. So you have mass pushing in being balanced by energy being created pushing out. So when the star comes to the end of its lifespan, it's coming to the end of its lifespan. A really massive star is coming to the end of its lifespan because it is now no longer able to make energy pushing out. And the force that is left is the gravity of the star pushing in. And so when that supernova happens, energy is no longer being produced in the center, the mass of the star collapses in, and then eventually all that energy will end up rebounding, make the explosion of the star expanding out. However, with that collapse coming in, you have an insane amount of pressure that is being put on the center of the star. And based off of how massive the star is, one of two absolutely crazy things will happen. One is you'll create a black hole, but everybody knows about black holes. They're every sort of thing. It's the second thing that will happen, though, is if it's not big enough in order to create a singularity, to create a black hole, all of the electrons that are flying around in the core of the star will get crushed onto the protons that are hanging out in the core of the star. And that electrons getting crushed onto protons create a giant ball of neutrons. And that is what is left over is a neutron star. And it's one of the densest things in the universe. Imagine an object that has the mass of the sun, as much matter that the sun has, being pushed into an object that has the volume of a small town of Hilo. And that's how massive a neutron star is. That's what a neutron star is. It's incredibly, incredibly massive. They also spin incredibly fast because they are spinning with the same momentum that the star had when the star was big. And when you put it that small, that object that has the mass of the sun, but the volume of a small town, is spinning oftentimes 300 times a second.
300 times a second is a lot there, but that's, most of them are not quite that fast.
That's, that might be the higher limit sort of thing. Usually at least 30 times a second.
Yeah, 10 on the order of 10 to, sort of the tens of times a second is sort of the nominal. Most of them spin about that rate.
But anyway, this was all just to describe neutron stars. What a kilonova is two neutron stars hitting each other. And what's crazy about kilonova is that the concept of a kilonova, of two neutron stars colliding with each other and hitting each other and making a lot of energy, was largely theoretical until 2017. Prior to 2017, we thought that they happened, but we never directly observed them happening. We never were looking in the right place at the right time in order to watch it happening.
And we didn't have the right tools.
In 2017, a big thing was LIGO, and our detection of gravitational waves. With by detecting kilonova first with gravitational waves to point us where to look, we are then able to use our optical light to then look at them with our optical light and observe the very first kilonova. And that was only in 2017, which is not even 10 years ago. And now it's a regular feature of one of the things that we're observing of these events that 10 years ago was something that was purely theoretical, which is just mind-blowing to me.
My favorite thing about kilonovas is essentially what the universe gets from them. So, as a little bit of background, the universe starts out in the Big Bang with basically two elements. You get hydrogen, which is normally what happens when you have a proton and a neutron, and you have helium. About 75% hydrogen, about 25% helium. That's all you have. Tiny bit of lithium, which is element number 3, but that's it. The amount of lithium you have isn't even worth counting at this point, and there's nothing else. So you and I, the observatory, the island, the Earth, are made of very little helium, and a lot of things that are different from hydrogen or helium. You're made up of carbon and oxygen. You're made up of phosphorus and nitrogen. And where all of those things, they didn't start in the universe, so where did they come from? Well, they came from massive stars. Those high mass stars at the end of their life will go through increasingly aggressive, energetic fusion energy reactions in their core, trying to stay alive. And they will generate some of those things up to about the size of iron, a little bit of stuff beyond that. But that doesn't explain things, elements that are as heavy as gold or uranium, or lead. It doesn't describe half the periodic table.
Mm.
So what we hypothesized that the conditions were right around a kilonova explosion to generate a lot of this. And so what was really remarkable in 2017, after the amazing thing of one, finding a neutron star collision in the first place, two, being able to actually observe it with visible and infrared telescopes afterward. But what we were able to do with those visible and infrared telescopes is actually look at the elements present. By doing spectroscopy, we could find out what elements are present in that kilonova debris. And sure enough, as predicted, we saw lots of those big metals. We saw lots of those heavy metals, things bigger than iron. And so it's enough for us to say this is one of the major sources of those large elements. So, so kilonovas are incredibly crucial for making up a lot of the bits of the Earth. And I think that's really one of the coolest things, is because we've gone from this condition of not knowing what the universe was made of to knowing what the universe was mostly made of and not understanding where the rest of the universe came from, to now having a much more complete picture of where all the stuff in the universe comes from.
Can we slow to what's it?
So
490,
Aaron and Emily, we're at
37.
just at the end of our session, but perhaps we could do another quick
I
check-in
said-
with Layla and Denise about, I hear they're slewing to a new target. Maybe we could check in with them and then wrap up this awesome session.
Oh yeah, I did. Yeah, so now we are going to start our GPP testing, which is the new software we're trying to implement, and it's been going on all week, and we just finished observing this kilonova, so now we are slewing to the next target.